So before we go to mechanical waves, I want to go through few things. There are mainly two types of waves. One type is what we are going to learn in this lesson, which is called mechanical waves. And the other kind of waves are electromagnetic waves. So I'll call it EM waves, electromagnetic waves. So now I'm going to give few examples of each. So I think you all are more familiar with these EM waves. Light. So light is a EM wave. What else? UV, ultraviolet or heat. Then infrared, X-rays. So all of these familiar stuff are EM waves or electromagnetic waves. And mechanical waves, an example for mechanical waves will be sound. Then earthquakes, the waves that you get during earthquakes and stuff. Then musical instruments, the strings in musical instruments. So all of those are mechanical waves. So there should be a difference between the two, right? There should be a fundamental difference between the two types. Does anyone know what's the main difference between these two types of waves?
The mechanical, you can feel the vibration.
Yeah, what else? Any more answers? Yes, mechanical, you can feel the vibration. So EM waves. So I got to answer longitudinal versus transverse. So longitudinal versus transverse waves are a part of mechanical waves. So mechanical waves can be divided into two more parts that we will learn today later. So EM waves, so this is the main difference. They do not need a medium to travel. In other words, they can even travel in vacuums. And mechanical waves, they do need a medium. So they need a medium. So that is why light can travel like from sun through the space even without an atmosphere to our atmosphere, right? That is why we get light. If EM waves needed a medium, we will never ever get sunlight. So EM waves do not need a medium, but mechanical waves need a medium. In other words, it needs a solid, liquid, or some gas phase to move. So it needs some medium to travel. Okay, so you all kind of have idea what mechanical waves are. Now let's dig deep into this. So there are a few things that you have to know about waves. So these are very common things to any kind of waves. So now first look at the characteristics. So there are few terms that you have to know. What lambda is, what T is also called the period, what frequency is, and what amplitude is, and at last what velocity is. So a wave is something which propagates energy, right? For example, sound. Let's say you are here and you are speaking. So yes, you are speaking. So sound waves, sound energy travels this way, right? So I don't know, like it. So waves is a mechanism where energy travels. So you will need that part when we look at this velocity. But before that, let's figure out what lambda is. So what is lambda? Lambda is the distance. So it is a distance measured in meters. It is the distance between two identical points in a wave. So here between two crest, I can't say that word, so I'll call it peaks. Okay, so between two peaks or between two of these minimum points or any two identical points, even two places like this. So lambda is the distance between two identical points in a wave. Okay, so it is called the wavelength. What is a period? What is T? It is the time taken for one lambda. Let's say our wave is like I said before, waves are propagating, right? So from this maximum point to next maximum point, how much time did it take? So it is the time per one lambda. Okay, time taken per one lambda, or you can even say time per revolution, time per one circle. In other, basically it is time for one lambda. Okay, so you are okay with T. So if you know T, F is easy. Frequency is the easiest if you know T. Frequency is 1 divided by the period. In other words, how many lambdas how many lambdas per second? That is what it really says. How many wavelengths do you pass per 1 second? Okay, 1 over T. And what is the amplitude? Amplitude is the maximum distance a particle travels. So when a wave propagates, so you will see later, when a wave propagates, actually the materials will not travel very far. Materials will only oscillate. So in some materials, material like a particle here will go up and down. So in some materials, they will go back and forth. So materials really don't travel very far. They will not go with the wave. They will only oscillate just to transfer the energy in the wave. So we will see it later. So this amplitude really is a quantity defined for a particle, like for one location. For example, here, what is the maximum vertical length this point moves? So in other words, this is your amplitude. Okay, so amplitude is the distance between a maximum to this midpoint or the equilibrium position. In simple harmonic motion, you remember amplitude? So from maximum to equilibrium position. So here also this is an amplitude. Okay, so we kind of know what these things are now. This is the other thing we have to know, velocity. So this velocity right here can be found using this equation. This equation gives you a relationship between velocity, frequency and lambda. And can anyone guess? I think y'all might know it, might not know it. What is this velocity? Is this the velocity your wave propagates? So wave propagate, or the velocity of a single particle. So what is the answer? A or B? What is this velocity? You can guess. It's okay. You don't know the answer. I got one answer for B. Is any A answers? So I got one for A, two for A. Okay, so A. Okay, so let's see. So like I said before, the main purpose of a wave is to propagate energy, right? So what it actually does is, it takes energy, let's say it's a string and you are giving it a pulse from here. You are doing this. You are giving a wave from this side. So the energy is going to go this way, right? It's going to do this and go this way. The velocity right here gives you the velocity of energy propagation. In other words, how fast the energy moves this way, or how fast your peak points move this way. But the actual material really doesn't move, right? So if you consider the rope, let's say this is a rope, the rope will go only up and down. This point will only just go up and down. It doesn't really move this way, right? So this velocity that you get by substituting this equation is the velocity of the wave propagation or the energy propagation. How fast the energy moves. Okay. And another important thing is this V velocity depends upon the properties of the material. So V depends on the properties of the material. So if it was a wire, if your wave is going through a wire, the velocity will depend on the properties of the wire. It will depend on the material, it will depend on the tension, it will depend on the mass and the length of the wire. It will not depend on the frequency or the lambda. So that is something very important. So you can use this equation to find the velocity, but velocity is determined by the properties of the material. Is it clear? What I really want to say is V depends on the material. Okay. So here are two problems. I want you to do them and tell me the answers. And always when you do these problems, especially problems like this, draw your wave. Draw the wave and mark what they are talking about. And then you will not go wrong. Okay. A fisherman fishing from, okay, he observes that it move on a climb up and down, taking, okay. So I'm going to draw what they're saying. So to go from up to down, so they're talking about two positions like this, right? So from here to, sorry, here it has taken 2.4 seconds. So what can you tell about this time? Is it t or is it something else? Is it t? Is it the period? Have they given us the period or they have given us something else? So very good. They have given half of the period, right? We know period is the time between two similar points. So if they gave us the time for this from here to here, then that will be the period. But they have given us half of a period, right? See, from here to here is half of this whole length. So the period will be 2.4 multiplied by 2. They have given us half of a period. To get the period, we have to multiply it. Okay. Now we have the period. Now let's read again. He also estimates that the distance between adjacent wave crests is 48 meters. So that is correct, right? So he has measured lambda correctly. Distance between two similar points. So lambda he has measured correctly and it is 48 meters. Okay, we have t, we have lambda, we have to find the speed. We know speed of the wave is given by v equals f lambda. Since we have t, we can easily figure out f, right? F is 1 over t. So now I'm going to substitute the values. F is 1 over t, t is 4.8, lambda is 48. 48 divided by 4.8 is 10 meters per second. Sorry, okay. So always draw what they are giving. Then it is easy to figure it out. Otherwise you might take this as t directly. Okay, part A is done. Part B. Second one. A wave moves on a string with wavelength lambda and frequency f. So I'm going to write an equation for that. V equals f lambda. A second wave on the same string has wavelength 2 lambda and travels with the same velocity. So it has the same velocity. We don't know the frequency. That is what we have to find. So I will just write f2 for that. And the new lambda is 2 times lambda. So velocities are equal. So what I'm going to do is I'm going to equate the two. F lambda is equal to F2, 2 lambda. Lambda get cancelled. F2 is equal to F divided by 2, 0.5 F. The answer is A. So in this problem, even if they did not tell you this part, so in this problem, they say they travel with the same velocity, right? Even if they did not tell that part, you should be able to figure it out. Why? It is the same string, right? It is the same string and they haven't changed the string. And you all know velocity depends on the medium, right? So if the medium, any properties of the medium wasn't changed, we will not change. So in this problem, they have made it easy. They have said velocity is the same. Even if they did not tell that, you should know that. Okay. Okay, so I will move to the next one. So the next part is energy of a wave. So if you remember what I said before, I said your wave propagates with some velocity, remember? And particles in the wave will move either if it was a transverse wave. So we will learn about the two types of waves later. If it was a transverse wave, particles will go up and down. If it was a longitudinal wave, your particles will go like this. So whatever the case, your particles motion is very limited. It either goes up and down or just moves like this. Okay, so these particles either go like just moves like this, up and down, like this. Or if it was a longitudinal, it will go like this. But basically they will not travel far away. Okay. So this particle motion follows simple harmonic patterns. So these particles move like simple harmonic motions. Okay, so that is the kind of problems that you will get. And we know in simple harmonic motion, energy, the maximum potential energy is given by half K A squared. So if you remember from physics 121, in simple harmonic motion, you had this equation, half K A squared, and A is the amplitude. Okay. So although I write it, I said it is potential energy, it is the total energy stored in the particle, right? Because maximum, it is the maximum potential energy. Even if it transfer into kinetic energy or a mixture of potential energy and kinetic energy, still the maximum value will not change, right? So this is the total energy of a particle in your wave, half Ka squared. Okay, so that is how we get this equation. Okay, so y'all, I hope y'all are okay with this equation. And now I'm going to erase this and go to the next part. So the other thing that you have to know is intensity. Intensity is the power per unit area. So it is defined as the power per unit area. And you all know power is given by energy over time, right? Energy divided by time. Energy in unit time is your power. And the other question I have is, why do they have this thing here, 4 pi r squared? I said intensity is power divided by area. Why do we have this 4 pi r squared? So I got the correct answer, because your energy or the power spreads like a sphere, right? For example, assume that there's a tiny device here, it gives out sound. So what happens? Sound waves go all around it, right? So whether you stand here, here, or here, you still get to hear the sound, right? So sound waves propagates along a sphere, in a sphere, all around it. So the intensity, when you are going to find the intensity, you have to divide power by the area of a sphere. Area of a sphere is 4 pi r squared. Okay. So you will see that the intensity that you are going to hear will decrease as you are far away from the source. That makes sense, right? You have let's say you have a loudspeaker here. When you are far away, you can't really hear it. The intensity is low. When you are closer, you can hear it well. So that is what it means. Okay. So here I have 3 proportionalities. So I got these proportionalities from this equation. Intensity depends on the or is proportional to the square of amplitude. How do I know that? Because intensity is proportional to power, right? Power is given by energy over time, and we know energy has this a squared term. So that is why intensity is proportional to square of the amplitude. So this is amplitude, okay, not area. Intensity is proportional to the square of area. Amplitude. Okay. Amplitude. And again, intensity is inversely proportional to the square of the distance. It's an inverse square law. And lastly, I have this equation. Here in this equation, what I have done is I have combined these two. See, in this two, IA is proportional to A squared, proportional to 1 over R squared, right? So I'm looking at this part. And I just took the square root of both the things. So I get A is proportional to 1 over R. So why did I write these proportionalities? I wrote this because in problems, knowing these proportionalities is useful. Why? Because you can quickly turn these proportionalities into equations. So I can turn this proportionality into an equation like this. I1, so when we are comparing stuff, I1 over I2, A1 squared divided by A2 squared. So see, I just quickly converted this to this equation. So I'll do the same thing to this one, okay? So I1, so where should I have R1? It should be in the denominator, right? Because it is inversely proportional. If I have I2, R2 should be here. Another equation. So when you know the proportionalities, it is easy to compare between few scenarios. So you really don't have to write this equation twice. Instead, you can directly put this or this. Okay. Okay. So I will move to the questions. So in the first problem, it is about energy. So you can do the problem. I'll give you time and don't get confused with this. They're asking maximum kinetic energy. We know kinetic energy, potential energy. If it is maximum, all of them are equal to half Ka squared. Okay. Although it is the equation for potential energy, when we are talking about maximum, it is the same, right? Okay, so draw a diagram and figure out what they're talking about, whether this is A or something else, and then tell me the answers. The bug on a surface is observed to move up and down the total vertical distance of 7 centimeters, lowest to the highest point. So what are they talking about? So this bug was in this lowest point has moved to this point, right? In other words, what is the distance the bug moved? It goes from negative way to positive way, right? In other words, the total distance that they have given is two-way. See, lowest to the highest point. So from here to here is the distance they have given. So they have given 2A. So I wrote A1 to show that it is the first instant is 7 centimeters. So your A1 is half of 7, which is 3.5 centimeters. So after some time, now that distance has changed to 4.5 centimeters. So again, 2A2, the second amplitude they're talking about, 2A2 is 4.5. So your A2 is half of 4.5, which is 2.25. Okay. Now we have the amplitudes. Now it's easy, right? We just have to plug into this equation. So even if you mistakenly plug the value of 2A Instead of taking A, still you will get the answer. The reason is because they are asking for a factor division. This factor 2 will get cancelled. So even if you didn't do this, then just took, if you took at 7 and 4.5, still you will get the answer. Okay, so E2 is half K A2 squared. E1 is half K A1 squared. So half K and half K get cancelled and you are left with A2 squared. What is A2 squared? 2.25. 2.25 squared divided by 3.5 squared. So you will get the answer 0.4104. 0.41. So I haven't done any unit conversion here because if I convert units, it will get cancelled. So even if you do unit conversions, you will still get the same answer. So energy is in joules here. Okay. So the units are here joules divided by joules. So here you don't have any units, but energy is given in joules. Okay. Joules divided by joules. Since they're asking for a factor, the factor has no units. Okay, this one, the intensity of the waves from a point source at a distance d is I. So they are not changing anything, they are only changing the distance, right? So now what I'm going to do is I'm going to use those proportionalities. So your answers are correct, B. So I'm going to use the proportionalities to do it. So you remember this proportionality. Intensity is inversely proportional to the square distance. So I'm going to use this to build an equation. I1, I2, R1 should be in the denominator, right? See, inversely proportional. R2 should be in the numerator. Okay, so I have an equation. What are they asking for? So they are saying initial distance is D and the intensity is I. So R1 is D. And we have to find the distance when I2 is 2 times I, right? D nu, so I'll write D nu squared. What I just did was I substituted for I1, I2, R2 and R1. Okay, so we need the new distance. So I'll keep distance here, the square here, and take everything to the other side. I divided by 2I, D squared, I get cancelled. So D nu is given by the square root of this whole thing. D divided by root 2. So your answer is B. So are you okay with this? Yes. So if you have time at home, like try to practice these proportionalities. So in this lesson, it's very easy if you work with proportionalities. Or if you are not okay with using this, what you can do is you can use this equation, okay? P divided by 4 pi r squared. So you can write this equation twice and get it like the normal way we do. So instead of R, you can put D. And for the second scenario, you can do this 4 pi d mu squared. So you can divide the two equations or solve them to get nu d. Okay, both the methods are correct. Okay, now we are going to look at the next part. What is the next part? We are going to look at the two types of mechanical waves. You all know what mechanical waves are. There are two types of waves in mechanical waves. We know this already. One is transverse waves. So in transverse waves, in both the cases, you all can see that energy goes this way, right? Or the wave propagates this way. So here what this person is doing is he's oscillating the wire like this, in this direction. And because of the oscillation, the wave slowly propagates towards the wall, right? So this is the direction of propagation. Even in this one, that is the case, right? He's doing this, oscillating the wire this way, and that energy slowly goes through the wave towards the wall, right? So in both the cases, propagation is this way. So do you agree with the direction of propagation of energy? Yes. But can you see the movement of particles is different? So in this one, if we look at one point of the string rope, you can see this will go up and down, right? It will not go this way. So it will not go this way. It will go up and down. So when the particles move perpendicular to the direction of propagation, so I will call V. So V is this way. The velocity, the direction it moves or propagates energy. So if the particle motion is perpendicular to the direction of propagation, we call it a S wave or a transverse wave. If your particles move along the same direction, so if I consider a point like this, what's happening is it will go like this, come back again to this side like this. So it will go in a motion like this way, like this. Can you see that the particle and the wave are moving in the same direction? Although the particle is not really moving, it is oscillating in the same direction, like this. So we call these sort of waves longitudinal waves or P waves. So sound is a good example for longitudinal waves. So that is how sound propagates. So you cannot see waves like this, right, when you speak. So it kind of compresses air like this. That is how sound moves. Okay. Okay, so you all know these two types. The reason why I showed this was to introduce you to these two equations. So this is the most common type, transverse waves. And I'm pretty sure that you have seen this equation before. Velocity of a transverse wave on a stretched string or a cord. So something like this, a wire. Okay, so the velocity a wave moves in a stretched, so this word is very important, stretched string or a cord is given by this formula, and this Ft is the tension of the rope or the wire, and this mu is the mass per unit length. So how would you find it? You divide the mass of the rope by the length of the rope. Sometimes they directly give you this value, mu. And this is the most common type of problems you will see. Even in the lecture, I think they did problems on this. But in your textbook, they have given the equations to find this as well. So if there are longitudinal waves can travel in solids and liquids or gases, so it can travel in anything. If it is a solid, this is the equation. V is equal to root E over rho. This E is the elastic modulus. It is a constant. So if they ask you to find it, find V, they will give you that value. Okay. And rho is the density of the solid. So if your longitudinal wave travels in liquid or a gas, then your equation is very similar, but instead of elastic modulus, what you have is bulk modulus. I have forgotten to put bulk. So this B is the bulk modulus. It is also constant for the medium. Okay, bulk modulus divided by the density of the gas or the liquid. So the equations, they rarely ask, but just know that there are equations like this. Okay. So if they ask a question, use the formula sheet for this equation and do it. So I just wanted to tell you that there are equations for longitudinal waves as well. Okay, so here are two problems. Very easy. And you will see both are from transverse waves. Do it and tell me the answers. So these two problems are easy, right? They are just substitutions. So piano string, so it's a string. Equation is tension divided by mu. Tension is 1350 and they have directly given us mu, right? Mass per unit length 0.0050. So when you do this, you should get 520 meters per second. So you really get 519 point something. So in correct fix, it is C. Okay. So in this one, so there are two scenarios happening, right? So in the first one, tension divided by mass over length. This is the first case. So when you get things like this, so can you see this is a division even under a division. So M divided by L. So what you can do is you can write it like this. You can take this L to the denominator. Okay. So let's see what is happening. So this is the initial case. And the second one is V2. They have not changed anything, but they have increased the mass, right? So if I take the 2 out, 2 comes out, and TL over M is your initial velocity. 1 over root 2 is 0.7. And this is P. So your answer is P. Okay. I think you all are okay with this. So here is another problem. This is a little harder, but not that hard. So try to do it and tell me the answer for the first one. Okay, so I will start it. So it seems like a lot of you are having trouble finding it. So first step is draw what is happening. So there are two children and there is a string, right? They are sending signals along a cord and the mass of the string is given by 0.5 kilograms. And they haven't given us the length, right? They're asking us to find the length. They want us to find the length or the distance between the two kids. These are the two ends. And they have given the tension as 35 newtons. What else have they given? Also, they have given the time taken for the wave to go from here to here is 0.55 seconds. Okay, let's see what is happening. So as the first step, I'm going to write the equation that I know. So we know how to find the velocity, right? Velocity is given by tension divided by mass per unit length. But they have only given us mass, right? Not the length. So this is the equation m over L. So I just write L here. So if I substitute the values, what I get is T is 35, M is 0.5, and L we don't know. That is what we have to find. So this is one equation. I still haven't used this, right? I still haven't used the time they have given. So how can I use the time? Do we know any equation which combines time, distance, and velocity? Yes, right? Velocity is given by distance over time. You remember this equation? Velocity is given by distance over time. So the velocity from here to here can be also found using this equation, right? From here to here, our distance is L and the time taken is T, 0.55. So both of these equations talk about the same thing, right? So can we equate them and try to find the answer? Can you equate the two and tell me the answer? Try to solve it slowly. I will also solve it here. So when I simplify this, I get 8.3666 at least still in the square root. And in this side, I have L divided by 0.55. So as the next step, what I'm going to do is I'm going to bring this root L to this side and take this 0.55 to the other side. So 8.3666 multiplied by 0.55. So that is in this side of the equation. And in this side of the equation, I have L divided by root L. So what do we get when we divide L by root L? You can just put a number and see. For example, 2 divided by root 2. What do you get? So you know L is made up of 2 root L's, right? Root L times root L gives you L, right? So when root L get cancelled, one of root L's get cancelled, you are left with root L. 8.3666.55. So what I'm getting is 4.6017 in this side, and in this side I'm left with root L, because L divided by root L is root L. So if you want to make sure, what you can do is you can put a number and see. 2 divided by root 2 will give you root 2. Okay, so we need L, right? So to get L, we take the square of both sides. So 4.6017, when we take the square, we get 21.17. In correct sig figs, this is what we get. So did you understand this part? So they always combine things like this. So part B. So part B is the same thing, but they have given length, right? So they have given the length. They're asking you to find the time. What can you do? First, you can find V, right? Because they have given the length. Using this equation, M over L. Tension is 35, length is 2, mass is 0.5. So from this, you can get the velocity. Okay. And you know the velocity. You can find the time now, right? Time is distance over velocity. Distance is 2 meters. Velocity we just found 11.83. So when you divide the two, you should get 0.17 seconds. So I will give you time to copy it down. Or if you have questions, you can ask me. So are you okay with this? So this is a little hard problem. Not really hard, but they combine few things together. Okay? Okay. So this is the last part we are going to do today. It's not hard. It is about reflection and transmission. Okay, so yeah, these are two parts. So I draw a line in the middle. So first we look at this set AB, and then we look at this. This is not hard, okay? So this is about reflection of waves. For example, let's think that a wave is going this way. So this is the velocity that we know how to find, V equals F lambda. O T root mu. So this is that velocity. So this wave goes and reflects at this hard surface. So in other words, this is a fixed surface. This is like connected, this wire is connected to this corner. So at this end, wire has no freedom. It is a fixed boundary. Okay. So at a point like that, your wave will reflect back, but now it will be inverted. Can you see its peak is on top here. So that is how it comes. And when it reflects, it has inverted. Okay, so that is one kind of reflection. When your wave goes and hits a fixed boundary or a hard thing, this is what's happening. It reflects, but with a phase change. It flips, or in other words, a 180-degree phase change. Okay, so that is one case. The other case is, now you don't have a very fixed boundary, you have a free boundary. So here it has the freedom to move, right? So when your string has the freedom to move, what happens is your reflection does not flip. It will not have a phase difference. So it comes and goes back, but with zero phase, no phase change. Okay, so reflection is turning back, right? So there are two kinds of reflection. Okay, now let's look at a scenario where you have reflection and transmission. Transmission means going forward. It transmits. So assume that these are two pieces of wires. This is low density. This is high density. High density means more mass, right? More mass per unit length, more mu. Okay, so here we have an incident wave and it comes and now it hits a hard surface, right? It has the freedom to move, but it has less freedom than before because this is a high density place, high density wire. So when it reaches a high density wire, it reflects back with a phase change, just like this scenario. See, just like this scenario. So that is why your reflected wave has a 180-degree phase change. So part of it reflects and another part transmits. Transmits means going forward without any change. The only change will be the amplitude because it cannot have the same energy, right? Half of it reflected. So only some transmitted. So your amplitude will be smaller. And the other important thing is frequency does not change. It is the same frequency. Okay, this is another case where it goes from high density to low density. So high to low. So now this wave goes and it meets this end. So this end is like a free boundary, right? Because this is a very thin low density wire. It has more freedom to move. So your reflected wave will be with zero phase change, just like this one. Okay, and transmitted wave similar. Transmitted wave means goes forward. There's no phase change happening to transmitted waves. Okay, so why did I put this up today? Because I wanted to tell you that reflection is what reflection is and what we call reflection echo. You know echoing, right? Like when you say something, it comes back to you. So that is because of reflection of waves. So in problems, when you see the word echo, that means they're talking about reflection. Okay, something goes, hits something and comes back. Okay, so can you quickly tell me the answer for the first multiple choice? Okay, I'm getting the correct answers. So it is C, right? Wave travels along a thin cord and then moves to a thick cord, right? So low density to high density. So we know when it reflects, this is like a hard boundary. So it has a phase change. So something which goes like this will reflect back with a phase change. And we know transmitted waves, it doesn't matter whether your boundary is high density or low density, it goes as it is. Reflected returns inverted. transmitted is right up. Okay. So I will do the last problem with you. You all also can start. A sailor strikes the side of his ship just below the surface of the sea. He hears the echo of the wave reflected from the ocean 2.4 seconds later. So here is your ship. So here's the ship. And the sailor strikes it somewhere. And he hears that sound back. He hears the sound echo. He hears the echo back after 2.4 seconds. So echo means what? Echo means something going in and reflecting back, right? Echo means like it's not the initial sound, it is the reflected sound that he will hear. Okay, so it will go deep into the ocean, strike the end of the ocean and come back. That is how he will hear this sound again after 2.4 seconds. So in the first part, they are asking you to find how deep is the ocean. So they have also given us the speed of sound in water. So how can you find it? So this is a very simple velocity is equal to distance over time problem. We know the velocity or the speed of sound in water, and we also know how it travels, right? So if the depth is L, how much distance did this sound travel within this time? Did it travel L distance or 2L distance? Echo means like something going in and coming back, right? So these problems are very common and very tricky. So the total distance the sound traveled within this time is 2 times L or 2 times the depth of the sea. Okay, so this is the important part here. So velocity of sound in water they have given 1500. Distance is 2 times the depth. Time is 2.4 seconds. So length or the depth. So it's a depth. Okay, depth of the sea is 1500. 2.4 divided by 2. So I have got 1800 meters for this part. So this is a very common type of problem. Okay. And in the next part, if he repeats this process at a point where the ocean is 225 meters deep. So now he repeats doing that. Still the same thing, right? Some sound goes in, hits the depth and comes back. So I'll call it L2 for now. So it travels this distance and they're asking how much time did it take. So velocity is distance over time. We have to find the time. So what is the distance it traveled? 2 times the depth, right? They have given the depth as 225. 2 times 225 is the total distance sound traveled. Velocity is a property of water. So it is a property of your sea. This 1500 given. So when you do this, you will get 0.3 seconds.